what I'd like to talk to you today is actually titrating acids and bases. This is part 7 of a multi-part series on acids and bases. You can find the rest on my YouTube channel, General Chemistry Talks with Dr. T. But we're going to start by titrating a strong acid with a strong base. And just to understand that, what I've got set up here is I basically have the titration apparatus set up on the left, so you can see the base is going to be added. That's what we're going to load in here is base. What's going on inside the solution I've tried to depict up here. This is kind of an expanded view of what's going on in there. So you can see right now I put a strong acid in solution, so the protons are free away from the counter ions. So these are chloride ions right now. And as the base is added, you're going to see how it interacts, and consequently we can figure out the pH. But the starting point on the titration of an acid with the base is, because it's a strong acid, whatever the concentration is immediately the concentration of H+. Take the negative log of that, you have the proper pH. Now when I start adding base, you can see the base coming in here. It's going to interact with the protons. It leaves behind a counter ion, which is a chloride ion in this case, which is neutral. And so any strong acid will leave behind a neutral conjugate base. So as you start to titrate, you add more base and it gets rid of one of the protons. And basically what I'm showing you is if at any moment you had to stop and figure out the pH, well, really whatever the original molarity of the acid and the volume of the acid minus the molarity of the base that's being titrated in times the volume you've added, that'll give the remaining protons. And then you have to readjust, because every time I add base I'm increasing the volume, so you have to readjust for the total volume as you move along with. This is the generic formula by which I'm finding the pH as I keep titrating. So I keep adding base. pH keeps rising. This should be linear if you were tracking it directly, but remember that you're taking the pH, which is not the direct concentration, but it's the log of the concentration. So this is an exponential function now. Now this last amount of base added is the equivalent amount of base to the number of protons that were there. So you can see as it comes in, it's going to literally cancel out the last proton. So at this point I have water and neutral salt, so that leaves us at the pH of 7, right, which is the autoionization concentration of protons in water, i.e. neutral water. Now if you keep, that's called the equivalence point, and if you keep adding base, all it's going to do is basically now be looking at the pH of a strong base in water. And once again, we know how to deal with that with this formula where we say, okay, well, the base is in excess, so I take the moles of the molarity of the base times the volume minus the molarities of the acid times the volume that got neutralized. And then I have to remember I still have been adding base all this time in some sort of volume, so the volume has been increasing the entire time, so I got to divide by the final volume. But that's the basic principles behind how the curve will look, how you could calculate the pH in any time. Keep in mind that if I solve for this, I'm going to end up solving for the OH minus, the hydroxide concentration. So I can do negative log of that. That'll be POH, and remember that subtracted from 14 gives me back to the pH. And away I go. So now let's do a variation. Now let's titrate with strong base again. So we're going to, all through these demonstrations, just load strong base up in the burette. And then the burette, as it adds to this solution, this time we're going to add it to a weak acid, in this case acetic acid. So if I was to see what was going on in this water right now before any base had been added, I would have an acetic acid solution in water, which by definition, if acetic acid is a weak acid, very little of it has disassociated. So the bulk of it would still be together as acetic acid, which does not affect the pH of the solution. the small amount of it that does disassociate, that is what creates the pH. We've learned in class that that can be approximated by taking the square root of the Ka for acetic acid times the concentration of acetic acid. That Ka for acetic acid is 1.75 times 10 to the minus fifth. Find that in your Ka table. So we start adding base. Now this is really important to see what happens. Here comes a base. It interacts with the strong acid. It pops free an acetate ion, which is, by the way, a weak base itself. So I haven't freed up any protons, but I have created a weak base every time a base comes down that I've titrated in a little bit of the hydroxide ion. So here comes some more hydroxide ion. Hits the acetic acid, frees up the conjugate acetate ion, which is the conjugate base. And you can see that this would just keep going on and on. But if at any time in here I needed to find the pH, I could use the Henderson-Hasselbalch equation, because at this point I have both weak acid and conjugate base in solution. And what we've learned in class is the way to find the pH when you have both weak acid and conjugate base playing against each other is you set it up according to this equation. Take the pKa of acetic acid plus the log of, now this is going to be the conjugate base concentration, but keep in mind the way the conjugate base showed up was every time, right, a base came in like so, that created a conjugate base. So consequently you can just figure out how much conjugate base is present by taking the molarity of the base times the volume of base added. But then you need to divide it by the acid concentration that's remaining. Well, how much did you start with? Minus how much base which was added, which neutralized it. And you'll consequently will be able to find out the pH at any time. And this is a unique situation right here where I've added the same equivalence of base as I have weak acid left over. So as I've got it drawn here in this picture, it's 4 to 4. In that case, the concentration of the base that's created and the concentration of the acid are the same thing. The log of 1 in essence, which is 0, which means that at that point the pKa is equal to pH, and that always happens right here in the middle of this. What we call this the buffer zone when we're titrating this, because we're using a buffer equation to solve the pH at any time. Okay? And that's the moment where these things are equal. We go on, we keep titrating. And then, of course, at some point we had enough base, so we actually hit the next amount of base added is actually the equivalent point, right? That's where you've actually put exactly as much hydroxide in as you have a weak acid. So now I get a pH, and the way to figure out how to find the pH at this moment is actually simplify this down and say, look, I have no protons because they all got tied up and turned to water. I created though conjugate base throughout, so now I'm really looking at a conjugate base problem. So the way to reframe this is, what would be the pH if I had this concentration of conjugate base sitting in water? So that particular formula, the one that's similar to this, right, where the hydroxide ion equals the Kb times the amount of base that's present, conjugate base that's present. Well, the way you find the amount of conjugate base that's present is that all came from the molarity of acid that was in there originally times the volume of acid originally. It's now been diluted by the titration, so you got to put the volume total, take that times Kb, that's OH. If you needed to turn that to pH, negative log of this, that'll give you the POH. Subtract that from 14, you got the pH. All right, so that's the equivalence point. Now, we continue to add base. At this point, it has no protons to attack, So now you have hydroxide in solution. Now you might be tempted to get into a intellectual wrestling match and go, wow, okay, I got base that's created by base present, and I've got conjugate base, and it's got an equilibrium. What's the final pH? Well, the nice simplification about this is the hydroxide is so much more concentrated than any base that the conjugate base would create. Because remember, this conjugate base only makes things basic because it's able to deprotonate a little water and leave a hydroxide behind. So that's almost insignificant compared to the amount of hydroxides that are getting dropped in there every time you titrate. And so that is what drives the show. So you can simplify the pH down at this point by just simply calculating how many hydroxides have been added above what was used to neutralize. And if I think about that formula, it's pretty straightforward. Hey, here's the total moles of base I've added, right? Total moles of base I've added minus the total moles of acid that were neutralized. That gives me the remaining base I've added divided by the volume total. That's the hydroxide ion concentration. Once again, you still need to convert it back to hydronium ion concentration and then take the negative log of that. Or if you want, take the negative log of this, subtract it from 14 to get the pH. All right, the last scenario. Now I'm going to titrate weak diprotic acid with the strong base. And this is the same sort of trend that would happen with any diprotic acid, but most diprotic acids are actually weak acids, so that's kind of helpful. Sulfurous acid, H+1 rule means that this is a weak acid. And so to start off with, the pH of the solution it's just a weak acid problem. If I drop this many equivalents of weak acid in water, what would be the pH? We can do that, and that, once again, it's a weak acid, so only a few of those deprotonate or dissociate. Calculation is very straightforward. In this case, it's the K1 you use because that's the first deprotonation of a diprotic acid. Right? Now you start titrating. I didn't put the base titrator in this picture so it didn't get too, it's going to get fairly complicated. I just wanted to simplify the picture. Whenever that first base hits, pulls off a proton. This leaves behind hydrogen sulfite, which according to the pKa is still a weak acid. Start adding more base to it. I'm kind of doing this a couple equivalents at a time. As you know, it's just going to keep attacking protons in there. Anytime though in this titration, if you needed to find the pH at any time, it's still back to Henderson-Hasselbalch equation. So at any time you can use the Henderson-Hasselbalch equation to solve the pH. And once again, don't get confused in the fact that it's diprotic acid. Just consider it as if the single deprotonation is a weak acid going in solution. So the amount of base that's been added is what created all the conjugate base. The amount of acid that's remaining is what goes on the bottom. You start with the full amount of acid started with minus the amount that was neutralized. Plug and chug, and you can have the pH at any time in the solution. Alright, so you just continue to titrate in the base, and remember that as the base hits one of these diprotic acid, it just creates the conjugate acid. Once again, the same idea holds that when you're halfway through this, when the conjugate base is equal to the amount of conjugate acid, this becomes 1 over 1, log of 1 is 0. The pK1 equals the pH anytime in the middle of these buffer zone calculations. So we keep adding base, and now at this point we've actually hit our first equivalence point where we put in as much base as there was diprotic acid. So at this point the pH is determined by that 1, and I'm going to just back that up a little bit. The pH is determined at this point when you're at the equivalence point by this, H2A. In this case, this is the hydrogen sulfite anion, right? And that actually is a weak acid, which if you let it sit in solution, the bulk of it will stay together, but some small equivalent will deprotonate, and that is all that drives the show to figure out the pH at this moment. So it's the same equation that you used earlier, only you use the K2, you use the HA minus form of it, right? The hydrogen sulfite is what you would use in here with the K2, and you plug and chug and solve, and that's how you find the pH at that equivalence point. Then you move on, and the hydroxides come in, they start to take off the second proton. So you enter a second buffer zone, and you can imagine the second buffer zone still is going to use the Henderson-Hasselbalch equation. The only difference is now you have to walk your way through. This is the second deprotonation, so you're using the pK2. It's a log of A2 minus, in this case the sulfide anion, over the hydrogen sulfite titration. And away you go. Same thing happens. You get into that middle of the buffer zone. These concentrations of A2 and HA are equal. At that point, the K2 equals the pH. It's just if you were doing this, actually graphing this, you could go to the middle of the buffer zone and approximate what the pK2 is. So you keep working on that. And for those of you who are in calculus, this ends up being convex down and convex up, so that inflection point is actually where that pK1 equals the pH. And so that's a useful point if you're have a good enough titration. So we keep on working on this, and then at some point I add enough hydroxide ions to get rid of the last proton. And so now we're just left with the sulfite anion, and this is just water, so we've completely neutralized this weak acid and left behind the sulfite anion, which is in and of itself a weak base. So now it just becomes a problem of, okay, well, what's the pH at that equivalence point? Well, once again, I tried to show you that in this diagram. If I had a weak base, I dropped it in just pure water, which in essence I have, well, some small amount of it's going to disassociate the water, create small amount of basicity. So here at this step, I really got to work with the K. It's what's called the KB2, which in essence is taking that sulfite. If you could just find the hydrogen sulfite 2, which basically can then be divided into 1 times 10 to the minus 14, you're going to get this KB2. That times the amount of sulfide anion is going to give you the hydroxide ion concentration, which you can then turn to POH, as we've talked about throughout this video. Beyond that, any hydroxide that's added is going to be running the show. It's going to be more significant than the small amount of hydroxide created from just a few equivalents of this sulfite that's still sitting around in the water. So from now on, you're basically just using the concentration of base from hydroxide added. And if you had to get back and figure that out, it's the moles of sodium hydroxide times the volume of sodium hydroxide. That's what's creating all this hydroxide, minus the amount of hydroxide that was totally neutralized. Now in this case you need to use 2 equivalents of the acid, because we're talking about the second proton coming off. And so now let's practice. I've got about 5 questions. There's a lot of practice work in here, and I'd like for you to just get used to using these kind of equations. Why don't you stop your video, write down these problems, try and work them out on your paper. Now I'm going to warn you ahead of time. It asks about, for example, benzoic acid, and it asks about a succinic acid. Well, you're going to need your Ka table to do that. And if you don't have a Ka table, you can Google it to get the K1 and K2 of these materials. And then stop the video, try and work out the solutions. When you're done, you can turn this back on and you can check your answers. Okay, let's see how we did. Starting with the strong acid titrating the base. What's going to be the pH at these different volumes? This is very similar to the graph I showed you in slide 2, so you can run back. The keys I'd remind you to doing all the problems that are on this homework set are Identify the strong and weak acid base. HCl is a strong acid, for example, titrated with sodium hydroxide, a strong base. Okay? Do the molarity times the volume, and then compare the acid to the base to see whether the resulting solution is acidic or basic, because that's going to drive the show as far as, how you're going to decide this. Just for example, right here, obviously I have added no base, so it's all acidic. Here I've added 20 mils of this base, but I already have 40 mils of acid, so it's still acidic. Okay, 40 mils of base, 40 mils of acid. Now we've hit equivalence. And then when you're into this situation, you got 50 mils of base, 40 mils of acid, you're in the basic zone. So you need to do that on all these problems, because that's what decides what formulas you should use. And also keep in mind, I've been titrating in base, so that's always increasing the volume. So you always got to do your calculations relative to the new volume. So let's get started with the easy one first. We're going to do the strong acid, strong base titration. In the first step, it's just basically a strong acid in solution is immediately the H plus concentration, negative log of that, that's your pH. Second problem, now it's still acidic, so you take the quantity of acid minus the quantity of base, right? So acid's 0.2 molar, you got 40 added, minus 20 mils of the base. The catch is divided by the total volume. And now remember, if you look back on past videos, it'll remind you that, look, when I take molarity times volume, I should do this in liters. But when I divide this by 1,000, divide this by 1,000, and then the bottom I'm also dividing by 1,000, those thousands cancel out. So in other words, you don't have to convert it back as long as your numerator and denominator are consistent in the volume units that you're using. Anyway, you solve this, you get an H plus concentration 0.067. Calculate pH minus log of that. Whenever you're titrating a strong acid with a strong base, you're creating neutral salt, so consequently, if you hit the equivalence point, the pH is 7. The last step, the base is in excess, so you use a similar setup like this, only now you're taking the base minus the acid divided by the total volume. You solve it, you get the OH minus, but remember that is not the pH. That's not the key to finding the pH. So what you can do is take the negative log of that, that gets you the POH, subtract that from the water of 14, and that'll give you your new pH at 12.3. If I graphed it, same thing, start off with the acid concentration, equivalence point is 7, base, it's very straightforward. The main points being, I know the original acidity, I know where the equivalence point is, and then that's kind of the key points I want you to pick off of these graphs. So anytime I saw a graph that I had a pH 7, I could make an assumption I'm probably titrating a strong acid with a strong base, unless I happen to have a weak acid or something that has a strange equivalence point where the conjugate base of that actually is very close to 7. Alright, so here's the next scenario. Now I'm going to titrate a weak acid with the strong base. And I want to know what happens when I have the following volumes of sodium hydroxide. I look online, or I look on my Ka table and see that benzoic acid has a pKa of 4.2, which means it has a Ka of 6.28 times 10 to the minus 5th. First problem, at that point it's just a weak acid problem. Ka times Ha times square root. I get a pH of 2.45. All of this is set up correctly. All right. Second problem, I'm still having acid in excess. So now what I got to do is, and here's where you have to understand the theory, because remember, when you still have acid in excess, the base that got added, all it does is create a conjugate base. So when that hydroxide comes in, it creates a conjugate base. So now we're going to use the Henderson-Hasselbalch equation. We just plug and chug. A big reminder here is whatever the base on top and the acid on the bottom, that calculation has to be done first before you take the log of it. All right. Get done with that, you get a pH of 4.2. Get to part C. At equivalence, right, all that's left is the conjugate base, which in this case is benzoate. But don't forget, when you set it up, you got to divide it by the total volume. So basically what I did was I said, okay, I've got the OH concentration at that point. We're going to do the square root of the Kb times the concentration of the base, right? And remember, if I knew the Ka, I could find the Kb, because if the Ka is that, I divide it into 1 times 10 to the minus 14, so the Kb is this, 1.59 times 10 to the minus 10. I take the Kb times the concentration of the conjugate base that's been created, and the way you figure that out is by how much acid was there originally times the volume of acid originally divided by the total volume. That'll get it diluted properly. I get an OH concentration of 3.99 e to the minus 6. I take the negative log of that immediately. It's 5.4. That, when subtracted from 14, is the pH. Get down to D. When I look in this situation, I actually have an excess of base. So really, it's the sodium hydroxide is a significant player that creates pH. All I have to do is figure out how much sodium hydroxide is left residual. So I take the moles of sodium hydroxide added total minus the moles that were neutralized by the acid divided by the volume total, and that's what it'll look like to solve for the concentration of base. But once again, that is not going to lead me to pH until I can take the negative log of that and subtract it from 14 and get 12.3. Now if I regraph this, all I can do is take these points that I've learned. Look, the starting pH. I know that midway through the buffer zone is actually going to be the pKa of the acid. So that's one point I could put on there. And then I can just take that conjugate base in that new volume, figure out its pH. That gives me a nice point for equivalence. And everything will pretty much have this shape. This is approximated. That's why it doesn't really have that inflection point like it should. All right, last thing, talking about the diprotic acid. We don't do tons of calculations here, but what I'd like you to be able to do is sketch it out, knowing some of the points. And some of the important points are, first off, look on your Ka table, get your pK1 and pK2, go ahead and turn those into K1 and K2. In order to find the original solution, all you have to think about is, this is just succinic acid, a single deprotonation. It's a weak acid problem. You can work it first that way. And I know that I have a K1 of 6.21 times 10 to the minus 5th. Take that times the molarity of the original acid. Take the square root of that. That'll give me my H plus. Negative log gives me the pH. That's my starting point. The first equivalence point. Well, what do you have when you get to the first equivalence point? The succinic acid has been fully deprotonated, so I have succinate ion, or anion, right? And that particular thing, as we do the shortcut designation, is HA minus, right? Consider a weak acid problem where I just drop that in water. I would take its K2, right, times the concentration. I got to adjust for the full volume, which is 40 mils of that divided by the total volume. Sulfur H plus, I get 4.81 e to the minus 4. The pH on that is 3.32. And then the second equivalence point, now what we've done is we've fully deprotonated succinic acid, and we've got a succinate anion, the A2 minus. And if I was thinking about dropping that in water, it's really like a weak base. So I cannot take advantage of this number, but I can divide that into 1 times 10 to the minus 14 and actually have the Kb for this, right? And so when I do that, divided by that, I get 4.33 times e to the minus 9. And so now I can just work it like it's a weak base problem. with the Kb, this concentration. But when I get to my second equivalence, remember, I had 40 mils of acid. It's diprotic. After 40 mils of base added, I've deprotonated once. After I add 80 mils, I've deprotonated twice. So if you sum up all the volumes at that point, it's 120. Find the hydroxide ion concentration, 1.7 e to the minus fifth. Solve for the pOH. And then once again, you can make an adjustment back to pH. You get 9.23. And so now I know that second point. I also know that the center of the buffer zones are going to be basically 4.21. Center of this buffer zone is going to be 5.64. So I have enough points to work off of to get a nice graph. So I hope this has helped you. You should run through these videos and work some homework, and that will strengthen your abilities to know how a titration works. And this is really about how an acid interacts with the base. It's as opposed to just characterizing the molecule itself or characterizing the solution itself. It's the chemical reaction of the acid with the base and the resulting pH.